This lesson, we're going to talk about how to perform function operations. So when we're adding, subtracting, multiplying, and dividing more than one function together. The one thing that we're going to talk about consistently is how to find the domain of these new functions after we add, subtract, multiply, and divide. So what I wanted to go over real quick is two ways that our domain can be limited. First of all, anytime you have an even root function, so if you have a square root or a fourth root or a sixth root, something with an even root, remember we cannot take the square root or fourth root or sixth root, any even root of a negative number. So what's underneath the radical has to be greater than or equal to 0. So if you have something underneath an even root, like x plus 6, for example, we cannot take the fourth root of a negative number, so we would take x plus 6, and we would say that that has to be greater than or equal to 0, and then we would solve. So when I solve this for x, I get x is greater than or equal to negative 6. So the domain for this function right here is x has to be greater than or equal to negative 6. Anything bigger than negative 6 or negative 6 would work. But if we tried to plug in negative 7, for example, we would be taking the fourth root of negative 1, and that's an imaginary number. So this first example, the domain would be x is greater than or equal to 0. But if there's anything more than just an x underneath that even root, just set what's underneath the radical, the radicand, greater than or equal to 0, and solve. So that's one way the domain can be limited. The other way a domain can be limited is if we have some sort of quotient. So you're looking for denominators. Denominators. Because in math, we can never have a 0 in the denominator. So anytime you have an x in the denominator, you have to think about what number could I plug in for x that would make that denominator 0. So in this case, 0 would make the denominator 0. So we would say x can be any number except 0. Or if it looked a little bit fancy in the denominator, like 2x plus 5, for example, we would have to ask ourselves, okay, what would make the denominator equal to 0? What would make 2x plus 5 equal to 0? So when I solve this equation, I get, negative 5 halves would make the denominator 0. So x can be anything except negative 5 halves. So that would be my domain. So two things you're looking for that limit the domain: even roots and denominators. Anything else, and your domain is just all real numbers. So let's start with addition. When we are adding functions, when it says f plus g of x right here, that just means f of x plus g of x. And with addition, order doesn't really matter, but we're going to take f of x, which is x minus 4, plus g of x, which is x squared plus 3x. And when adding things together, you're really just combining like terms. So f plus g of x would be x squared plus 4x minus 4 when we combine all of our like terms together. So that's f plus g of x. And our domain, because if you're looking at the original f, the original g, and our new function f plus g, there are no quotients and there are no even roots. So our domain is just all real numbers. Next, we're going to evaluate that sum when x equals 3. So we're going to take what we just found and we're going to plug in a 3 wherever there is an x. So 9 plus 12 minus 4 is 17. So when we evaluate when x equals 3, we get 17 as an answer. Let's do one that's a little bit trickier. So now we're adding with radicals. But f of x, when we take f of x plus g of x, they both have a cube root of 2x. So really, it's kind of like combining like terms. Our coefficient here is an invisible 1. So we have 1 plus negative 11, which is negative 10, times the cube root of 2x. That's what we get when we take f plus g. And our domain, there are no quotients and no even roots. A cube root is an odd root, because 3 is odd. So our domain, again, is all real numbers. When we find f plus g of negative 4, that just means we're going to take that function and we're going to plug in negative 4 for x. The cube root of negative 8 is negative 2. So negative 10 times negative 2 is 20. So there's two examples of addition. Let's do 2 examples of subtraction as well. The only thing that's different with subtraction is we're going to have to distribute our minus sign, especially with these polynomials when I take f minus g. And order matters. Pay attention to whether it says f minus g or g minus f. And the first thing I need to do is distribute that negative sign to everything in g, because we are subtracting g. So that means we're subtracting x cubed. It's going to turn into a adding 3x squared minus 4x and a plus 2 before we then go through and combine like terms. So f minus g of x, or f of x minus g of x, we have 2x cubed and x squared. There's a negative 4x. And a 5 and a 2 together makes 7. There's f of x minus g of x. If we evaluate that when x is 2, or another way of saying that is finding f minus g of 2, that just means we're going to plug in 2 wherever there's an x. We're evaluating the function. So we get 2 cubed times 2 plus 2 squared minus 4 times 2 plus 7. So looks like 19. Let's try another subtraction one. Again, we have radicals here. Oh, and I forgot to mention on this one, but neither one of our functions has a quotient or an even root. So once again, our domain is all real numbers. But on this next example, we do have even roots. We have square root signs. So our domain is not going to be all real numbers on this one. When we start by subtracting, we have 3 times the square root of x minus negative 10 times the square root of x. Make sure your radicals match. So we have root x and root x. So we can combine the 3 minus negative 10 to make 13 root x. That's what f minus g of x is, or f of x minus g of x. And we do have even roots, both in the original functions and in our new function that we created. So our domain is x has to be greater than or equal to 0 to keep what's underneath that radical non-negative. And then lastly, we're going to plug in 4 then into that function we just found. So 13 times the square root of 4, or 13 times 2 is 26. When we have powers that are rational exponents, x to the 1/2 power, just keep in mind that that's the same thing as saying 4 times the square root of x. This is the same thing as saying 9 times the square root of x. So you can write them either way when you're adding and subtracting. If I leave them as 4x to the 1/2 plus negative 9x to the 1/2. They match, they're like terms, so we're just adding those coefficients together to get negative 5x to the 1/2. That's what f plus g of x would be. And then when we're subtracting, we would just have 4x to the 1/2 minus negative 9x to the 1/2. Similarly, we're combining like terms, but this time it's 13x to the 1/2. But the domain, if you rewrite the rational exponents as radicals instead, you can see that we have even roots. So for both of those, f plus g of x and f minus g of x, our domain is x has to be greater than or equal to 0 so that we are not taking the square root of a negative number. All right, let's try a multiplication problem. So I think the easiest way to start these multiplication problems is if we have the square root of x, like g of x here. I'm going to rewrite that as x to the 1/2 power. So then when I'm multiplying f times g, it's a little bit easier than to combine those bases together. So we have the same base, which is x. And our exponent rules say that when you're multiplying, you're going to add exponents. So we're going to take 2 plus 1/2. So if we get common denominators there, that's like saying 2 is like saying 4/2 and 1/2. So when we add those, we get 5/2. So f times g of x is x to the 5/2 power. Then we're going to evaluate that when x equals 9, so 9 to the 5/2 power, or if I rewrite that, that's the square root of 9 to the 5th power. The square root of 9 is 3, and 3 to the 5th power is 243. Let's go back through and state the domain. So whenever there is an even number in the denominator, we have an even root. So both in our final answer and in g of x, we have even roots, which means that our domain is x is greater than or equal to 0 in order to keep that radical non-negative. Another multiplication problem. So 4x to the 5/4 power times 2x to the 1/2 power. Already, just by looking at the denominators, I have 2 even roots here, which means our domain is going to be limited. If you were going to write that as radicals, those would be even roots. But when we have a multiplication problem, we are going to multiply the coefficients. 4 times 2 is 8. We're going to add the exponents on the two x's. So 5/4 plus 1/2 becomes 7/4. And then the domain is limited because we have even roots in both f, g, and f times g. There are even roots. So x needs to be greater than or equal to 0. And then we're going to plug in 16 for x. So I'm going to rewrite that as 8 times the 4th root of 16 to the 7th power. 4th root of 16 is 2. 2 to the 7th power is, let's see, 2, 4, 8, 16, 32, 64, 128. 8 times 128. We have 1024. All right, lastly, let's do a couple division problems. Division order matters, so pay attention if you're doing f divided by g or g divided by f. In this case, we have f divided by g. G has an even root, so our domain is going to be limited here. And now that we're dividing, there's an x in the denominator. So that's also going to limit our domain. So in division, we subtract exponents of like bases. So we have 6x to the first power over x to the 3/4 power, or 6x to the 4/4 power over x to the 3/4 power. 4/4 minus 3/4 is 1/4. So that is f divided by g of x. Our domain, like we said, is limited because even roots. So because there are even roots, x needs to be greater than or equal to 0. But also, because there's an x in the denominator, x can't be 0, or that would make the denominator 0. So that just means x has to be greater than 0. And then we're going to evaluate when x equals 16. So 6 times 16 to the 1/4 power, or another way of saying that is 6 times the 4th root of 16. The 4th root of 16 is 2. So that answer would be 12. One more. Again, we're taking f divided by g. Pay attention to which one goes on top and which one goes on bottom. This time there are no even roots, but there is an x in the denominator, so that is going to limit the domain. When we simplify this, 7 divided by 49 is 1/7, or we put a 7 in the denominator. And then when we subtract our exponents, on the x's, 5/3 minus 2/3 is 3/3. 3/3 is just 1. So we have x over 7. F divided by g of x is x over 7. Our domain, even though there is no x in the denominator in our final answer, there was an x in the denominator to get there. So x cannot be 0, or over here, the denominator would have been undefined. Our answer would have been undefined. So our domain, because there was a quotient, we do not ever want the denominator to be 0, so x cannot be 0 in this case. When we plug in 5 into that final answer, it's just 5 over 7. We're just taking x over 7 and plugging in 5.